We have finally studied enough physics where we now can take everything that we have learned and combine it all together into one problem. What do I mean by that? I mean that you will encounter problems which require to use kinematics formulas in addition to Newton's second law. So remember, kinematics is all about motion. So we're really talking about all the kind of Unit 3 stuff when we talk about kinematics. And Newton's second law is what we have focused on here in Unit 5. What we would like to be able to do is to solve problems that combine these two units together. Now, if you notice, Unit 5 always seemed to have the same kinds of variables. We always had acceleration, mass, and net force, and we were able to solve problems by using Newton's second law, F net equals ma. Now, Unit 3 had a lot of variables that dealt with motion, things like acceleration, initial velocity, final velocity, change in time, and displacement. And the equations that we used to solve those problems are the three equations of motion that deal with acceleration. Now, if you notice, there is one thing that we have in common between these two columns, and that is the acceleration. We can be given maybe some information about the motion of an object and be asked a question about the net force on that object. Because acceleration is present both with motion and forces, we just need to solve for that acceleration in order to be able to solve the problem. So let's do an example. A race car has a mass of 710 kilograms. It starts from rest and travels 40 meters in 3 seconds. The car is uniformly accelerated during the entire time. How big is the net force acting on the car? Hint, make a quantitative force diagram and write a net force equation for the axis along which the forces are not balanced. Well, the first thing we're going to do before we take on that hint is we're going to write out the knowns. So our mass is 710 kilograms. We're starting at rest, so our initial velocity is 0 meters per second. We travel 40 meters, so delta x is 40, and we do it in 3 seconds. Now we want to know how big is the net force acting on the car. So you see now how we've got, three different variables that deal with motion, and then we've got two things that deal with forces, and it's the forces that we want to answer the question for. So what we're going to do is we're going to start with all of this motion stuff to find the acceleration. Okay? So we're going to use motion to find acceleration. So we want to use an equation that has acceleration, vi, delta x, and delta t. And the equation that combines all of these things from Unit 3 is delta x equals vi delta t plus 1/2 a delta t squared. Then we can substitute all of the variables in. Our initial velocity was 0, so we don't care about that. And then our time is 3 seconds. So the only thing we don't know is acceleration, and we can use algebra in order to find what that acceleration is. It ends up being 8.89 meters per second squared. Now that we know the acceleration, we can find our net force. So we are going to find the net force with F net equals ma. So F net equals ma. We can substitute in what we know. We know the mass is 710 kilograms, and we know that that acceleration is 8.89 meters per second squared. So all we have to do is the algebra, and when you do the algebra, you end up getting, whoops, doing this on my calculator here, you end up getting approximately 6,312 newtons. So that's our answer. Combining Unit 3 and Unit 5 really is that easy. These problems, they're always going to be 2 steps. We'll show it to you by doing another example problem. Suppose that a 1,000 kilogram car is traveling at 25 meters per second. Its brakes can apply a force of 5,000 newtons. What is the minimum distance required for the car to stop? And then we're given that same hint. Well, the first thing we're going to do is we are going to write out all of those knowns. So our mass is 1,000 kilograms. We are traveling at 25 meters per second. We are braking. So braking is a force of friction. We can do that with 5,000 newtons. And we're trying to get this car to stop. So our VF is going to be 0 meters per second. Ultimately, we want to know what is the displacement to make that happen. So let's see what we got. Well, yeah, yet again, we have a couple different things. We do have a bunch of things about motion, right? VI, VF, and ultimately we want to find the delta X. But we also have mass, and we have a force. Because we want to find a quantity from the motion column, we should start with the forces to find acceleration, and then we'll go to motion. All right, so we will use F net equals ma to find the acceleration. So our F net, well, it's the unbalanced force, and when you're braking, your unbalanced force is friction. So really, we're saying that friction is equal to ma. So friction, we're going to give that a quantity of negative 5,000 newtons is equal to 1,000 kilograms times our acceleration. So we divide both sides by 1,000 to get acceleration by itself, and we find that the acceleration is negative 5 meters per second squared. Now we are going to use motion to find our delta X. So for motion, we have VI, VF, delta X, and acceleration. So we have to think which of one of our motion equations has those 4 quantities in it. And the motion equation that has those quantities in it is VF squared equals VI squared plus 2a delta X. So we'll fill in everything that we know. 0 squared equals 25 meters per second squared plus 2 times negative 5 meters per second squared times delta X. There we go. It's all algebra from here. And when you do all the algebra, you find that the displacement ends up being 62.5 meters. These 2 example problems show you that you can go from motion to forces, like how we did in this first example, or you can go from forces to motion. The problem-solving process works either way. How do you know what you need to do? Well, for this first one, we were asked a question about forces. So we needed to start with motion to find the acceleration. In the second problem, we were asked a question about motion, so we needed to start with forces in order to find the acceleration.